Hi everyone. In this video, I would like to now explain how to derive the OLS estimator, but in the context of a multivariate linear regression model. Let's start with the basics. Assume that now you would like to propose this linear model to explain your dependent variable yi using k regressors. So now the intercept is beta naught. Your first regressor will be x1, x2, and so on, right? So the coefficients of each of these regressors will be distinguished by the different subscripts. So all these are betas, but the subscripts correspond to the specific regressor. So the last one is beta k, xik. And of course, since this is the population model, we include the error term. Now, note that this equation tells you that for each individual, you are proposing this linear model. But that's for each individual I. One of the nice things about the matrix notation is that you can basically propose a similar equation, same model, but everything will be compact in vectors and matrices. That's convenient because you don't have to write all the betas, beta 1, beta 1, beta 2, beta 3, and so on. And also, you represent with matrix notation the data that you actually have in practice. That's very nice. So for example, in practice, what you will have is a vector of the dependent variable. No? So we're gonna call that one my, let me actually represent this in vector form. So suppose that all the observations that you observe for each individual I are clearly summarized by this vector with observations y1, y2, y3, and you keep going up to yn, because you have n observations. Clearly, this is a vector with n rows and 1 column. Now, I will follow the same equation, okay? Now, I will write a matrix which summarizes all the regressors. For example, my first element is, which, by the way, should be located in row 1, column 1, is the first observation for the first regressor, right? If you observe the next individual, you will have that for the same variable 1, x1, you have the second individual. The third individual, first observation, must be there. And you continue in the same fashion up to the n individual for the first variable. And you can do something similar for your second variable. Let me first list all the individuals, get the idea. So individual 1, 2, 3, up to n, for my variable 2, 2, 2, 2. Clearly, you will continue doing something similar to the second variable, third variable, up to your k variable. This is true for the second observation, variable k, or regressor k, third observation, regressor k, and I will do it in this way. The last one you will observe is for the n individual, and your K regressor. Now note that we also have a constant or an intercept in this multivariate linear regression mode, my beta naught. If you have a constant, you must include in this matrix a vector of ones. If you don't have the constant, don't include the vector of ones. Okay, is that simple? Now, suppose that you have the constant, which means that you include the vector of ones. This matrix now has dimensions n, because we have n observations, but the number of columns is not just k, it's k plus 1. The plus 1 is because of the constant, right? And we will multiply this matrix by a vector of parameters according to the population model, right? The first parameter is precisely my intercept, beta naught. The second one is beta 1, then beta 2, beta 3, and you will continue up to beta k, which means that this vector of parameters has k plus 1 rows and just one column. Makes sense. K because of the k regressors, and the plus 1 is because we are including the constant. But that's not all. We also have a vector that has n observations, and this is the vector of residuals, no? Epsilon 1, epsilon 2, epsilon 3, up to epsilon n. So this is n times 1. Now, if you compact all this information, because that's everything you have, right? If you compact this information in matrix notation, well, the first one is my vector of the dependent variable y. And this y vector has dimensions n times 1. And is equal to my matrix X with dimensions n times k plus 1, which is multiplied by a vector of parameters with dimensions k plus 1 times 1. And one of the things that we know from previous videos is that if there is a coincidence in the number of columns of the first matrix and the number of rows of the second matrix, then you are allowed to make this product, which is our case. So we are good. And of course, there is at the end a vector epsilon, which includes the error term. And this vector has dimensions n times 1. So when you make the product of your matrix X and your vector of parameters beta, you will obtain a resulting vector with n rows and 1 column. Clear, right? That comes from these two, which is precisely the same dimension that my vector of dependent variable has, and same for the vector of residuals. So it's basically the same stuff, right? Nice. Well, that's how you go from your regular linear regression model with multiple variables to a vector notation or matrix notation. The next step, now that we are here, the next step is to derive the OLS estimator in the context of a multivariate linear regression model. So we will continue using the vector notation, But one of the things that you must recognize now is that the new definition of the error term comes from the definition of the fitted values using matrix notation. So now, if you propose, because this is, in matrix notation, this is your population model, right? If you use this model, you estimate this model, you will obtain now a vector of coefficients, beta hat. And with that beta hat, you could estimate your dependent variable. The fitted values of this linear model is something that we are going to continue calling y hat, but it comes from the product of this matrix X, which only contains observations, right? And the vector beta hat. Beta hat is obtained using OLS. No? And I will show you how to derive that OLS estimator by hand. But for now, this is something that you must see immediately. The fitted values of your dependent variable come from this linear model, which means that now you could define your residuals as the difference between the actual values of your dependent variable and these fitted values. It's just facts. It's exactly what you saw before for the univariate case. No? It's not different than that. In fact, the new definition of the sum of the squares of the residuals comes from the product of the transpose of your vector of residuals and the vector of residuals. If you don't believe me, I will do it quickly. The transpose of a vector is a row with observations epsilon 1, epsilon 1 hat, epsilon 2 hat, up to epsilon n hat. Right? For each observation, you could obtain an estimate of the error term that we call the residual, right? And that's the transpose of the vector of residuals. What is the regular vector? Well, this epsilon 1, epsilon hat 1, epsilon hat 2, up to epsilon hat n. Can you make this product of these two vectors? Well, let's check. No? The first one has dimensions 1 times n. The second one has dimensions n times 1. Of course you can. In fact, the number of columns in the first vector matches the number of rows in the second vector. And the resulting product is just one number. It will be a vector of 1 by 1, which is just one single number. It comes from the product of epsilon 1, epsilon hat 1, epsilon 2, hat 2. I mean, epsilon hat 1 and epsilon 1 hat, which is the same, no? So epsilon hat 1 square. The second one comes from epsilon hat 2 and epsilon hat 2, which is epsilon hat 2 square, and so on. The last one must be epsilon hat n square. In other words, this sum or this product of epsilon hat transpose and epsilon hat is the sum from 1 to n of the epsilon hat squares, just as we saw before. So you will obtain the same. There is no difference. And that's, at the end of the day, your objective function, which is the one that you would like to minimize. You would like to minimize this objective function by choosing beta hat. Now, one of the things that I mentioned before is that by definition, this epsilon, this product of these two vectors, you know that is the sum of the squares of the residuals. But in matrix notation, each of the epsilon hats come from the difference between the observed values and the fitted values. But the fitted values, by definition, are x times beta hat. So this is my first epsilon hat transpose. The second epsilon hat is not transposed and is defined in a similar way. So I will rewrite this optimization problem as follows. The first thing that I'm going to do is to transpose the first vector, which is y transpose. Look at the properties that we went over last time. You are going to apply the transpose to each of the elements of this sum. And when you transpose the product of two matrices, you just transpose each of the matrices, but you have to flip the order. If you don't remember, go back to your notes. The second vector is the same. It's just epsilon hat, which by definition is what I have here inside the parentheses. It doesn't seem like, but that one is a beta hat. And before I start taking first order conditions, I will distribute this product. So the first, and you must be careful with the order of the matrix, because here the order matters, right? First you have your y transpose, and then you have y. Just multiply the first one times the first one. Next one, the first one, which is negative y transpose times x beta hat. And then what I'm going to do is the second one times the first one, which is also negative beta hat transpose x transpose y. And the last one is negative times negative, which becomes positive beta hat transpose x transpose x beta hat. So I haven't done anything yet. I just rewrote the main objective, or the objective function, right? Now I will take first order conditions. And you know that the first order conditions tells you that the derivative of your objective function must be equal to 0. Why? Well, because graphically the derivative is the slope of your objective function. You would like to see when the slope is 0, because that's when you find the minimum. So here we are going to use the definitions or I will say specific formulas that I introduced for the first time in the linear algebra review. One of those, most of them are pretty similar to regular calculus. For example, in the first term of this objective function, you don't really have any beta, right? So you're taking the derivative with respect to beta hat. So here you don't have beta, which means that that derivative must be 0. Now what about here? Well, there you have beta, and the moment you take the derivative of that second term with respect to beta, things are pretty much similar like in regular calculus. It's just negative y transpose x. The third term is interesting because beta there is transposed, and you are taking the derivative with respect to beta, not beta transpose. So this derivative is quite similar because you will keep these terms that you're practically considering as constants, but you will have to transpose them, which means that the moment you take the derivative, guess what? You will end up with the same expression as the first derivative. Super nice. And for the last one, you have to use the fourth property that I explained in that video, the linear algebra review. Here you have something similar to a beta hat square, right? It's like if you have beta hat square. It's not exactly the same because this is in matrix notation, but if you bring everything to real numbers, that will be something similar. No? The properties, in fact, or the derivative of this product of matrices is in fact, I would say, basically the same as the derivative of x squared with regular calculus. And that's because this matrix x transpose x is symmetric. If it wasn't, then the derivative will be beta hat transpose and the sum of x transpose x and x transpose x transpose. But you don't need that. It's I mean, officially, let's say, that will be the derivative. But since x transpose x is a symmetric matrix, it's like if you had it twice. Once again, go back to your note. So this will be 2 times beta hat transpose and your symmetric matrix. And according to the first order conditions, this must be equal to 0. I will rewrite the first 2 terms. Obviously, this is negative 2 y transpose x plus 2 times beta hat transpose and your symmetric matrix. I will do 2 things at this point. First, I will divide both sides of this equality by 2, and I will add on both sides y transpose x, which leads me to this expression, beta hat transpose x transpose x is equal to y transpose x. But the thing is that we don't want an expression for beta hat transpose. We want an expression for beta hat. That's what we would like to estimate. No? So it's very simple. What I want to do on both sides of the equality, it has to be on both sides because I want to keep everything unaffected. I will transpose both sides. Let me be 100% explicit on the steps. I will transpose the left-hand side, and I will transpose the right-hand side. Here, we're going to use our second property that I explained in the linear algebra review video. If you have the product of 2 matrices and you transpose them, you apply the transpose to each of the matrices, but you have to flip the order. X transpose X, which should be transposed, but remember, X transpose X is symmetric, times beta hat, transpose. And you know from one of those properties that I explained in previous videos, when you double transpose, that brings you back to the original matrix. In this case, my vector beta hat. Now the right-hand side is the same. We're going to use the same property. And the last step, I would like to pre-multiply. Everything has a specific order. You must be careful, right? I will pre-multiply by the inverse of this symmetric matrix because I want to get rid of this matrix on the left-hand side. So let me pre-multiply also the right-hand side. I'm going to leave everything unaffected. And now, this guy is the identity. The identity times my vector beta hat is just beta hat. On the right-hand side, now I have my symmetric matrix inverse times x transpose y. And this, my friends, is the OLS estimator in matrix notation. And that's it. Okay? That's how you derive it. All right. Well, I see you next time. Take care. Peace out.